All right, hello everyone. Welcome to our week 9 lecture and intro to analysis. This week we're going to talk about some topology concepts of the topology of the real line. And in particular, we're going to look at open and closed sets, limit points, open covers. We're going to talk about the Heine Borel theorem and prove some of it, and compact sets. And we're going to do lots of examples of each of these topics. So without further ado, let's get started with our first example, our first definition rather, open set. Okay, so what's an open set in the real numbers? An open set in the real numbers is open if for every element in that set, there's some positive delta such that the open interval of x minus delta to x plus delta is contained in the set U. And so what does this mean a little bit more intuitively? It means that for all elements in your set, there's some neighborhood that's centered at x, at your element x, so that that neighborhood is completely contained in the set. Okay, so sometimes I'll call this neighborhood right here, sometimes I'll call it the the delta neighborhood, and sometimes I'll refer to it as the delta ball centered at x. Okay, and it makes sense because if we have like x minus, let's say, we have some positive delta, and here's x right here, well, our neighborhood is going to be centered at x, and it's going to have this left endpoint is going to be x minus delta, and this right endpoint is going to be x plus delta. And so the distance from x to x plus delta is delta. And same thing on the other side, the distance from x to x minus delta is also delta. So that's our delta neighborhood, or our delta ball. Okay, and so I want to give you guys two pictures of this concept. The one-dimensional picture, which we're going to be talking about this semester, but also the two-dimensional picture, so you get the intuition of what I mean by ball, epsilon ball. So here's our one-dimensional picture. Okay, we have the real line. We have an open set U on the real line, which is just an open interval, as we'll see in a few slides. And let's say that we have some little x in our capital U, in our set. Okay, and so what this definition of open means is that I can always find some positive delta, no matter how small, so that when you center x in that little neighborhood around the little delta neighborhood, it's always going to stay within the set. Okay, and I have that picture here. I have this green as my delta neighborhood. And so like the point of this is that x could be really, really close to the endpoint of this open set. It could be really close to this orange thing right here. But this definition of openness says, hey, it doesn't matter how close x is to that endpoint, that orange spot. We can always find an epsilon neighborhood around it so that that neighborhood's completely contained in the orange. Okay, and so if we zoom in, to the neighborhood, what we're going to see is this picture right here. So we see x is centered in this little, I keep saying epsilon ball, and I eventually will say epsilon ball when we do have an epsilon ball, but it's a delta ball because I'm saying like the radius or the distance from the center to the edge is delta. Okay, so if we zoom in, we get this picture right here, and the point is that we have our orange that's really, really close, but it doesn't matter. It's still completely contained in that open set. And so likewise, we have a two-dimensional picture. And so here you can see why it's called ball, because it's literally if x is right here, then x is the center of this delta ball, And no matter how close x is to the edge of the set here, we can always find a delta radius small enough so that it's completely contained in that orange set. So now we have a definition of open, so let's give some examples of open sets. Wait, oh, I didn't show this part. Okay, I looked at my notes and I was like, wait, I didn't say this. But I said it out loud, okay? So if you have x in your open set, no matter how close to the edge, okay, I should have written open there, we can always find a little ball around it so that the ball is completely contained in the set, just like we did in the 1D picture and in the 2D picture. Okay. Moving forward, let's give some examples here. So the real line itself is open, okay? And so we're just going to use our definition to prove this, okay? And so the idea here is we can choose an x. So choose x in R. Okay, and so for any, so remember our open definition says that there must exist a delta so that the whole delta ball centered at x is completely contained in the reals. Okay, and so any delta will do this for us. So we can say that for any delta in the positives, right, positive real numbers, we have that the neighborhood x minus delta, x plus delta, is completely contained in the real numbers, right? To be explicit, we can choose delta as anything. We can choose it as 1, 2, pi, whatever, and all of those neighborhoods are always going to be a subset of the reals, right? If delta equals 1, then, you know, x minus 1, x plus 1 is going to be somewhere like this. That's definitely contained in the reals. If we have delta equals 2, x minus 2, x plus 2 is another subset in the reals, and so forth and so forth. Even if, you know, no matter how small we make our delta, if we have 1 over 10,000, like in this example, it's going to be a really, really tiny neighborhood right there, but nonetheless, it's still going to be contained in the real numbers. So we can assert that the real numbers are is an open set. Okay, so reals are open. The next one is kind of weird. So the empty set is also open. And it's open because there are no elements in it to contradict openness, okay? And so, like, in order for a set to be open, you know, every single element in the set has to have a delta neighborhood around it that's completely contained in the set. But there's no elements in the set to work with. So there are no elements in the empty set. And what we say here is we say that the statement is vacuously true. And what this means is that there's nothing to contradict openness here, okay? And so there are no elements in the empty set to contradict the empty set being open. So we say that this is vacuously true. All right, so empty set's open. Any open interval where a and b are real numbers are open. And why is that? Let's go ahead and draw a picture here. So here's our real number. Let's say this is a, and let's say that this is b. And remember, the definition of openness says that for any element in the set, let's say x, let's say our x is right here. For any element in the set, I can find a little neighborhood around that element that's still in the set, okay? And so to make this a little bit more precise, let's go ahead and take a look at the distance here. The distance here is going to be x take away a, right? That's going to be x take away a is going to be the distance here. And similarly, the distance right here from x to b is going to be b take away x. Okay, that's going to be that piece right there. And so to guarantee that we have a neighborhood that works, we can take our delta to be the minimum distance of this guy and this guy, right? If it's the minimum distance, then there will certainly be, there's certainly going to be a neighborhood around, like, centered at delta that is completely contained in AB. Okay, and so we're going to say, well, let delta be the minimum distance, so let it be minimum distance, then certainly we have that neighborhood is going to be contained in AB. And so the way that I've drawn it into, like, the way I've drawn the scale here, you can see that this guy is the minimum distance. And so what this is saying is, like, okay, so I can make a neighborhood with this distance because this is smaller than this distance. So it's certainly going to be, this neighborhood is certainly going to be contained in here, right? This distance x minus a is smaller than this guy. So that's the idea here. Every open interval is going to be open. Okay. And likewise, if we have the interval from a to infinity, this is open, and negative b to infinity are also open, and we can play the same sort of game with this guy. So again, what's the definition of openness? Just means that for everything in the set, we can find a little neighborhood that stays in the set, okay, that's centered around that element. So in this, let's say negative infinity to b, so here's negative infinity, and let's say this is b, and maybe we have the set a to infinity right here. Okay, so there's our two sets, and so, and let's say that x is right here. Okay, well, I can just look at the distance from x to the edge here, right, which is, well, actually, I'm gonna, yeah, okay, I'll call that, well, just to be consistent with my notes, I'll call this x prime, and I'll call this x, okay? And so, so this distance right here, if I look at the other side, like if I just, make it symmetric, there's a neighborhood, right? And so I can choose my delta to be this distance, and so that neighborhood is completely contained in the set. Okay. So more formally, let's make this delta prime to be consistent with my notes. So we're gonna take delta prime equal to the distance from b to x prime. Okay, so b take away x prime is gonna be that distance, and this is gonna imply that this neighborhood centered at x prime is indeed going to be contained in negative infinity to b. Okay, this is indeed going to be contained in negative infinity to b, right, because you can see it in the picture, okay? And similarly over here, we can look at this distance. Okay, so this distance is x take away a. All right, x take away a is that little piece. And so here we can take delta to be that distance. And this means that that little neighborhood, if we just make it symmetric with x in the middle, okay, we can see that that neighborhood's clearly contained here. All right. So we have x minus delta, x plus delta is indeed contained in there. And therefore, we have openness just by the definition of what it means to be open. Okay, let's look at a non-example. So you probably know this intuitively from all the classes that you've taken when you've seen these kind of sets. You know that anything with brackets on the endpoints is closed in the real numbers, and anything with parentheses is open. Okay? And so, you know, in that sense, the closed set from A to B is not open. Okay? It's closed. We'll see that later. Now, not open does not automatically imply closed. And and yeah, and a set being, yeah, okay. So I'll leave it at that. We'll talk about this in a few more slides, but there's a funny comment in the Cummings book that I want to talk about a little bit when we get there. But okay, let's move forward. All right, so by the definition of openness, we should be able to take any single point in our set and put a little ball around it that stays in the set. But we can't do that with closed sets, okay? And let me show you why. Well, with not every point in closed sets, right? The definition of open says that for every point we have this property. And so this is not open because, check this out. So we want to ask what I just said out loud. Does there exist a positive delta for which 1 minus delta, 1 plus delta is completely contained in 1, 2? And the answer is no. Nope. And why not? We can draw a picture here. Here's our real numbers. Here's the interval 1, 2. And we're interested in the point x equals 1. Okay, so this is my x equals 1. And so the question is, can I find a little neighborhood that stays in the set? And the answer is no, right? No matter how small we make our neighborhood, i.e. no matter how, or whatever, yeah, i.e. No matter how small we make our delta, we're never going to be completely contained in the set, right? We're always going to be outside this way. Okay, so this set fails the openness condition. Not open. Okay, here's a proposition. If you have a finite collection of open sets, then the union of each set in your collection is also open, and so is the intersection. Okay? On the other hand, if you have an infinite collection, and this is countably infinite or whatever, I mean, I just wrote countably, but this extends even further than countably infinite. Anyway, if you have a collection of open sets, an infinite collection, then the union of all of those sets in your collection is also open. Okay, so let's look at some examples of this. So, for example, we have an infinite union of open intervals. We know open intervals are open, and so this is open by our proposition, by the second part for infinite sets. Okay, what about this guy? So the intersection the intersection of 0, 2 and 1, 3, if we draw a picture of this, here's 0, 2, here's 1, 3, we can see that the intersection is 1, 2, right? And this is open by proposition 5.1, number 1, right? If we have the intersection of finitely many open sets, then that is open as well. So this is open. This guy is a finite union of open sets, so that is open as well. This guy is an infinite intersection. These are all open sets for each n, right? If n is a natural number, -1 to 1 is open, right? Open interval from -1 to 1. -1/2 to 1/2 is open, etc., etc. And notice that in our proposition, we don't say anything about, we say something about a finite intersection, but we don't assert that an infinite intersection is open, right? We only assert that an infinite union is open, but not an infinite intersection. And let's see why with this example. Okay. So where am I? I'm like looking at my notes. Let's see. Here we are. Okay. Yeah, okay. So if we draw a picture of what this looks like, this set right here, all right, we're taking the intersection of all of these UNs. So U1 is equal to -1 to 1, U2 is equal to blah, 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 -1/2 to 1/2, and we go in this pattern, okay? So U3 is -1/3. Okay, and we're trying to find the intersection of these sets. So here's -1 to 1, -1/2 to 1/2, and we can see where this is going, right? So what do all of these sets contain, right? What are all of these sets going to have in common as n gets large? All sets have 0 in common, right? In common. Because when n gets large, these little intervals are shrinking closer and closer to 0. They're never going to reach 0, so they're all going to have 0 in common. Okay, and so the intersection from n equals 1 to infinity of un is going to be 0. And 0 is not open, right? 0 is not open for the same reason that closed sets are not open. We can't find a little neighborhood around a single point. It's literally just a point. There's no neighborhood. Okay, so there's an example. All right, let's look at a theorem. I'm not going to prove it, but I just want to mention it just so we have it in our toolbox here. Every open set in the reals is a countable union of disjoint open intervals, where open intervals are of the forms that we talked about. So the real numbers itself, we have open intervals from a to b, -infinity to a, and b to infinity. Okay, and so the idea here is that, let's say we have, this open set. Let's say we have, maybe I'll do this in different colors. Let's see. So let's say we have maybe this guy, this guy, this guy, this guy, and this guy. So if we take the union of these guys, this is certainly an open set. And so this theorem is saying I can make this disjoint, and we can see that, we can see how. We can disjointify. I don't know if this is a real word, but whatever. We'll disjointify. And so if we do that, then, notice that, if we were to just cut out this picture right here, we still have all of this covered by these endpoints right here. Okay? And so the idea here is, so instead of, writing this nested set of intervals, we can simply write it like this. And so now, like up here, we didn't have disjoint intervals, but here we do. Okay, and so this theorem guarantees that we can always have that. So this is a countable union of disjoint open intervals. Okay, so Let's now talk about closed sets. So, a set is closed if the complement is open. Alright, so if the complement of the set is open, it's closed. So let's look at some examples. So as I mentioned before, any closed interval from A to B, where A and B are real numbers, is indeed closed. Because if we look at the complement in the reals, here's A, B, and if I just look at everything outside of this open interval, I'm going to be looking at all of this and all of this, and the union is open, right? So this is going to be negative infinity to A, and then from B to infinity. And I'll write this off to the side here. Equals A, oh shoot, yeah. Okay, so this equals negative infinity to A, union B to infinity. And this is open. Alright? Okay, so now we have something weird that's happening, and this is where I'm going to mention the Cummings book. He has a footnote in his book that says to... I'm trying to think what page it's on. I don't know. It's in this section. But you know, you can have sets that are both open and closed, and they call them clopen. And there's a funny video on YouTube of, I guess they took it from a movie or something. Or maybe it's not the real speech. I think it's an actor. But anyway, it's, you know, it's all in German. It's Hitler talking about something in German, and they put subtitles that talk about clopen sets, and he's really mad about clopen. So it's a funny video. You know, go look it up if you're bored. But anyway, so sets can be closed and open. And so two such sets are the reals and the empty set. So why are the reals closed? Well, if we consider the complement of the reals, that is the empty set, and we already said that the empty set was open, right, a few slides ago. And similarly, the complement of the empty set is the reals, and we also said that the reals were open. Okay, so the reals and the empty set, clopen. Okay, they're both closed and open. Okay, the single point 2 is closed. In fact, any finite set is closed, which we'll see in just a bit. And that's because the complement is open. Right? If we look at the complement of 2, everything except 2 in the real numbers, everything except 2, here's 2. So if we look at everything except 2, we're going to be considering negative infinity to 2, not including, union with 2 to infinity, and we know that these are both open, right? The union of open sets is open. Okay, let's see. Moving on. Our next definition here is limit point. Okay, so a limit point of a set is the following. We call a point X the limit point of a set A if there is a sequence of points A1, A2, A3 in the set but not equal to X. Okay, so all of these AIs are in A, but none of them are X. Okay, so that the sequence A sub n converges to X. Okay, so that's what a limit point means. It literally means, like, it's actually just what you think it means. It's like, we talked about limits of sequences, right? And so there's this sequence that has a limit, and none of the members of the sequence are the limit itself, and the entire sequence is living in a set, okay? So let's do some examples with this. So the first assertion here is that 0 is actually a limit point of the set 0, 3. So the claim is that we can find a sequence that's completely inside of 0, 3 that converges to 0. And indeed, there's lots of sequences that will do this. And one in particular is the sequence 1 over n. So consider a sub n equals 1 over n. Well then, a1 equals 1, a2 equals 1/2, etc. These are all in here, right? It's just like here's 0, 3, here's 1, here's 1/2, and so forth. It's never going to get to 0. It's going to get close. So all of these are in the set. So these are all in the set. And no, AI is 0, right? We're never going to have that this expression actually equals 0 for any n. Also, we know from our previous sections that we've looked at that this sequence converges to 0, and so 0 is a limit point. In fact, 3 is also a limit point. We can find a sequence in this set that converges to 3. In particular, 3 minus 1 over n, where n is a natural number, is completely contained in here. So yeah. Let's look at this example of a closed set. So 2 is a limit point of the closed set from 1 to 2. We can consider the sequence that is getting closer and closer to 2. Notice that each of these terms in the sequence is completely contained in 1, 2, right? If this is our real line, oh, I screwed that up. Let's see. Here's 1, here's 2, and so here's our line here. And all of these guys live in here, right? They're all really getting close to 2. They're all somewhere in the set. And none of them equal 2, right? And that's part of the definition, that none of these things in the sequence can actually be 2, the thing that it's converging to. Okay? And so clearly, or whatever, the sequence, maybe I'll put this sequence converges to 2, and none of the terms are 2. So 2 is indeed a limit point. So I have this note here that I want to harp on a little bit. Notice that in our first example, we looked at limit points that weren't in the actual set. Okay, so an open interval is not going to contain all of its limit points. On the other hand, a closed interval will contain all of its limit points. And we're actually going to show this now. Okay, let's look at this. So here's our theorem, and we're gonna prove this. So the theorem is a set is closed if and only if it contains all of its limit points. Okay, so we have an if and only if, so we need to prove both directions. Let's go ahead and prove the forward direction first. So we're going to suppose that A is closed, and we're going to show that this implies that it contains all of its limit points. All right, so I encourage you to pause the video, see if you can work this out for yourself, but let's go. So suppose A is closed. So just by the definition of closure, we know that this means that the complement is open. Okay, this is just the definition of what it means to be closed, is that its complement is open. All right, and so if we want to say something about limit points, we need to start by defining a limit point, right? We're trying to show that the set being closed means that the set contains all of its limit points. All right, so we're going to start by defining a limit point. So consider a limit point of A. Say this limit point is called L. Then, by the definition of limit point, just by our previous definition, there exists a sequence in A sub n, which converges to L. Okay, so that's just that's what it means to be a limit point. And we're trying to show that this arbitrary limit point that we defined is contained in A. That's what we're trying to show. Okay. Let's see. What do I want to do here? Oh, also, I want to say that also for all n, A sub n is not equal to L. This is just by definition of limit point. None of those terms are L itself. Okay, so how are we going to do this? We're going to proceed by contradiction. Okay, so what are we trying to show? We're trying to show that A contains all of its limit points. We defined an arbitrary limit point L, and what we're going to do is we're going to suppose, for the sake of contradiction, that L is not contained in A. Okay, so suppose, for the sake of contradiction, that L isn't an A. Well, what does it mean for L to not be an A? That means, well, we want to bring up this some kind of way, right? And to bring out a complement in the proof, I can say that L not being an A means that L is in the complement of A. It's the same thing. Okay, and now we're going to use the fact that the complement of A is open. Okay? Since the complement is open, by definition of openness, by the definition of what it means to be open, there is some positive delta for which the neighborhood centered around L is completely contained in the complement of A. Okay? So for which L minus delta, L plus delta is completely contained in that set. Okay, so we're just using the definition of a complement being open. There's some delta so that that neighborhood is going to be completely contained in a complement. All right. So here comes our next piece. So we already used this piece, that the complement is open. Now we also have this piece right here. Okay, we have the piece that the sequence A sub n converges to L. Now what does it mean for a sequence to converge? We have to go back to that definition where you were supposed to brew a pot of coffee and think about it for a long time. So the definition is this. Okay, so remember that our sequence converges to L. So what does that mean? So for all positive epsilon bigger than 0, there's some capital N, so that when you go enough far in the sequence, you're going to get close to L, right? Such that n bigger than capital N is going to imply that that sequence is getting close to L. And so the idea here is like, okay, we know that we know that let's see, what am I trying to say here? I see. So we're trying to show that there's a contradiction with our assumption, right? So we want to show that there's a problem here. And so to get the contradiction, to see the contradiction, we can bring in our delta into this definition. We're going to let epsilon equal delta. And so then there's some capital N for which this holds true, replacing epsilon with delta. Then we have a sub n minus L is going to be less than that. And so what does this mean by the properties of absolute value? This is going to mean that we have this is between negative delta and delta. So it's just properties of absolute value here. If we add L to everything, we get this. L plus delta. And so what does this mean? This means that A sub n is in my my delta neighborhood, right? Because it's between L minus delta and L plus delta. So this means that AN is in this neighborhood. Okay, and this is a contradiction. This is a contradiction because we assumed for each n, A sub n was in A. But A sub n is here, and that is completely contained in the complement of A. Okay, it's not in A. It's completely contained in the complement. So that's our contradiction. Okay, so this direction is done. Okay, so we've shown that closed implies that it contains all of its limit points. So let's go ahead and do the other direction. And so we want to show that a set A containing all of its limit points implies that A is closed. So we're going to do this by, we'll prove the contrapositive of this statement. And the contrapositive is logically equivalent to the original statement. So that's what we're going to do because it's easier, I think, to prove the contrapositive. So we'll prove the contrapositive. That is, we'll prove this. We'll prove that A not being closed implies A doesn't contain all of its limit points. So negate the conclusion and the hypothesis and switch it. It's the contrapositive. Doesn't contain all of its limit points. All right. Let's see how much room I have. Oh, I don't have a ton of room. Let's see. I think I'm gonna, let's see. I think I'm gonna just erase some of this stuff and move up. Let's go ahead and do that. I need a bit more room than I've given myself. Let's see where we're at on time. Okay. Okay. Alright, and I'll just rewrite it. It's fine. So again, we're doing the backwards direction, but we're going to prove the contrapositive of the statement. Okay. Okay, so this direction, prove the contrapositive. So we're going to show that A not being closed implies that A doesn't contain all of its limit points. All right, so what are we going to do? We're going to suppose the hypothesis that A is not closed. So suppose that A is not closed. Then, by definition of not being closed, the complement is not open. By definition, the complement is not open. Okay, and so what does openness mean? It means that every point in your set has a neighborhood around it completely contained in the set. So, being not open means that there is some point in the set, so that every epsilon neighborhood is not contained in the set. Or in other words, every epsilon neighborhood contains a point outside of the set. Okay, so that every... Oh, I keep saying epsilon. I hope you guys will forgive me. I meant delta. I'm sorry. It's just habit, I guess. Epsilon, epsilon, epsilon. Okay, so every delta neighborhood of X contains a point that's not in the set that is not in the set. Well, what does it mean to not be in the complement of A? Well, that means to be an A, right? And so, in other words, for every delta bigger than 0, this neighborhood contains a point in A. Okay, so I know that this was a lot to parse through, but we're just using the fact that A complement is not open and the definition of the complement. Okay, so now we're going to take a specific delta, right? Because this says for any delta bigger than 0, this neighborhood contains a point that's in A. So the delta that I'm going to pick to complete this proof, or the sequence of deltas, is going to be delta equals 1 over n, where n is a natural number. For each n, take a member of my sequence, a sub n, to be a point in A and x minus 1 over n to x plus 1 over n. Okay? Right? Because this assertion up here says that, okay, I take any delta that I want. I'm taking 1 over n to be my delta. Then I can find a point that I can find a point in my neighborhood that contains a point in A, right? And so I can always do this. And it not be empty. I can find a point in both the neighborhood and A, okay? And I'm going to call that point A sub n. And I'm going to form a sequence in this way. Okay, so we claim that the sequence, right, because we let n equal 1, we get something for n equals 1, we let n equals 2, we get something there, and so forth and so forth. So we claim that the sequence converges to x. since each a sub little n is in A, right, because of this, and x is in the complement of A, this will show that x is a limit point of A. And this will prove that, and because x was in A complement, this will show that A doesn't contain all of its limit points. All right? So let's go ahead and do this. So we're trying to show this. We're trying to show that our sequence here converges to x. So for each n, just by what I've underlined in blue here, maybe I'll underline it here too. For each n, a sub n is going to be in this neighborhood. Okay? So for each n, a sub n is in this neighborhood. And so by properties of absolute value, right, we can go from neighborhoods to absolute value just by what it means to, like, the absolute value properties, basically. So what does this mean to be in this neighborhood? It means that a sub n is going to be bigger than x minus 1 over n and less than x plus 1 over n. And this implies, by properties of absolute value, that a sub n minus x is going to be less than 1 over n. Okay? And so what's the idea here? We want to show convergence, and so we're thinking of this as our epsilon, right? To show convergence, we want to show that the distance here gets arbitrarily small. This is less than epsilon. Okay? And so, because we have this, let epsilon be bigger than 0, and we're going to choose, if we pretend for a second that this equals epsilon and we solve for little n, we get that little n equals 1 over epsilon, and so this is what we're choosing our capital N to be bigger than, right? If you guys remember that trick. Okay, so let that be given. By the Archimedean property, we can choose capital N in the naturals bigger than 1 over epsilon. Then n bigger than n implies, well, if we if we look at this, we have that this implies that n is bigger than 1 over epsilon, which implies that 1 over n is smaller than epsilon, right? And that's what we have up here, or that's what we want. Okay? So let me write this more formally. Then n bigger than n implies, so we have a sub n minus x. This is less than 1 over n, which is, right, this is always true. This is less than 1 over capital N because of this. Like, we just flipped the inequality when we take reciprocals. And this is less than epsilon. Again, taking reciprocals flips the inequality. Okay. And we're done. So, a sub n minus x is less than epsilon. So, x is a limit point. A limit point. And hence, A doesn't contain all of its limit points. Okay, and we're done. So that was the proof. Okay, here's another proposition that I am not going to prove, but it can be handy. So if you have a finite collection of closed sets, then the union of each of the sets in that collection is also closed. And if we have a countably infinite collection of closed sets, then the infinite intersection is also a closed set. Okay. All right, and now comes the open cover stuff. Okay, so let's talk about some definitions. So let's say that A is a set, then the sets U sub alpha, where alpha is an S, are a cover of the set A, if A is contained in the union of all of those sets. Okay, and I know that the notation is kind of confusing, so I just want to spend a little time talking about it, but once you see examples in practice, it's not such a big deal. So we call S the indexing set, and so like S could be the natural numbers, it could be the real numbers, it doesn't matter what S is. It's just some set to keep track of your U sub alphas. So like, for example, if S equals 3, then we would have the set U sub 1, U sub 2, right? I'm just looking up here. U sub 3. So each alpha is in the set. Maybe I should have written it like this. I should have written it like S equals 1, 2, 3. That's better. So each of these alphas is in the set. And so like if you had that your set was equal to natural numbers, then your U sub alphas would just be U1, U2, U3, etc., etc. It'd go on forever. So yeah, I know it's kind of like weird notation, but that's what it means. So let's look at some examples to get our hands dirty with this stuff. This collection of sets is a cover for the set 1, 3. And why is it a cover? Because the set 1, 3 is completely contained in the union of these sets. We can draw a picture to see this. So here is the set 1, 3, our set of interest. And then the other sets, maybe I'll do these in green. Maybe I'll do these sets in green. So 0, 2 is going to be, I don't know, like right here. I don't know. I'm not really drawing these to scale, but yeah. Okay, 1, 4 is going to be this open set from 1 to 4. And then 8, 9 is going to be somewhere over here. And so if we look at the union of all of these sets, so like the union of this guy, 0, 2, along with the union of 1, 4, which is all of this stuff, and then all of this stuff, this black is completely, so from 1 to 3 is completely covered by the union of those sets. Okay, that's why they call it a cover, because it's literally covered. Okay. All right, if each, so, you know, you can think about this. Let me see if I want to, yeah, I mean, and we can say it formally. We can say a little more formally, rather. 1, 3 is contained in the union of 0, 2, union, 1, 4, union, 8, 9. And notice we didn't even need 8, 9 to cover it. We could have got rid of that completely, but it doesn't really matter. It's like, okay, if the union covers it, it's still an open cover, even if there's like unnecessary stuff in there. So, yeah, this is our U1, our U2, and our U3. Okay? So another part of the definition, 5.4, is open cover. So this was a cover, but it wasn't an open cover because for an open cover, all of the sets in the cover have to be open. But here, this is a closed set. So an open cover means that each of these sets is open. Okay, and finally, our definition 5.4 concludes with the definition of finite subcover. So what does that mean? That means that if you have an open cover, it could be infinite. You could have an infinite collection of sets that cover a set. Like, we could literally say, you know, we could think of an infinite number of sets that cover 1, 3, for example. We could say, like, you know, negative n to n, where n ranges from 1 to infinity, covers 1, 3. Like, that is definitely an infinite set that covers 1, 3. But the point is, we don't need an infinite set to cover 1, 3. And we say that a subset of a cover could be infinite, like up here. A finite subset of a cover that still covers it is a finite subcover of A. So can you think of finitely many things here that would still cover 1, 3? Right? This, like, again, let me just write this here. So this guy is going to be the set negative 1 to 1, negative 2 to 2, and so forth. All right, this goes on forever. Okay, so the claim is that this covers 1, 3, but I can find a finite subcover. So I can pick out a finite set in this infinite set that still covers it. That's a finite subcover. But I can find a finite subcover, and it's not hard to do because you can just think about it. So here's 1, 3. And look at all of these things. You want to make your, like, you can make your n as big as you want. And so, like, what about 4? If n equals 4, this guy is actually a finite subcover of this. So let's write it. Because it still covers the set. And it's just a portion of the infinite sets, just a finite piece. I'm probably saying way too much about this, but hopefully this helps some of you guys see this. I remember when I first learned about this stuff, I was like, what are you talking about? Finite subcover? What? Yeah. So let's write it. So negative 4 is a finite subcover for this infinite thing, right? We just plucked out something out of this infinite cover that covers 1, 3. Okay, so those are some definitions there. All right, let's look at some more examples. Okay. So as I said, we can have infinite covers. Let's look at the set 0, 4, the open interval from 0 to 4. And we claim that this guy is an open cover. So, you know, I mean, you can think about it in this way. You can think, okay, well, I can let k get as big as I want. So the limit as k goes to infinity here is 0, and the limit as k goes to infinity here is 4. So it's gonna it's going to cover this piece. It's never actually going to get to 4 or 0, but that's okay because of the open interval. And this is just the set up here written explicitly. So that's an open cover. And the question I have for you is, can we do like we did in this example where we were given an open cover? We were given an open cover and we found a finite subcover. Can we do that here? And the answer is no. So the answer is no. And it turns out that being closed and bounded is the only guarantee for a finite subcover. How should I write this? Actually, I'm going to write it differently like I have in my notes. Okay, so being closed and bounded in R guarantees that every single open cover of the set has a finite subcover. Now, so here's the point. The point is that if we have an open interval, not every open cover is going to have a finite subcover. Some open covers will. For instance, like 0, 4 is right here. And certainly I can make up an open cover that's finite. I can say, how about -3, 5? That's an open cover of 0, 4, right? It's an open set and 0, 4 is completely contained in it. So yeah, we can find finite subcovers, but not every open cover has a finite subcover like this one does not. Let's look at some more examples. And I'm probably going to beat this like a dead horse or whatever, but fine. Just skip through it or don't watch. I don't know. But okay, so let's talk about another open cover. So as I mentioned, yes, we can cover an open interval with finitely many open sets. It's fine. Since our set here that covers 0, 4 is finite itself, it is itself a finite subcover. And moreover, there's actually another one here, and that's if we eliminate 1, 2, this is still going to cover 0, 4 if you were to draw it out on the number line. So this guy is also a finite subcover of C. All right, so now here's the closed and bounded case. All right, we've been looking at open and bounded sets, but now if we consider closed and bounded, it's a different story. Okay, and we're going to see that closed and bounded means that every open cover has a finite subcover, every single one we can think of. So let's look at this example. All right, so notice that we have this open cover. This is an infinite open cover because this piece has infinitely many sets in it, and it contains a finite subcover. And the finite subcover is if we just go up to the 6th element here, like U sub 6, and we adjoin or we union these guys, this is actually going to cover 0, 4 in its entirety. And let's see that drawn out. So let's go ahead and this is going to be a really rough sketch. But here's 0, 4. And let's say that, let's see, what am I doing here? I'm in the wrong place. Okay, there we go. Like looking at my notes, I'm like, oh, I'm in the wrong place. So let's say that this is my blue piece of the picture. Let's do a purple piece. Maybe I should have made this purple. Let's do this purple. Okay, so let's cover this thing. With my purple, I have negative 0.2 to 0.2. That's going to be like something like this. Again, rough pictures here, guys. 3.9 to 4.1 is going to look something like this. Okay, so that covers those little endpoints. And then this piece right here, if we go from k equals 1 to 6, we're going to cover the rest of this stuff. So it's going to overlap. Like we're going to have some sets that overlap here, and it's going to cover the rest of the stuff. So stuff like that. Okay, rough picture, but point is, if you have a closed set, or more specifically, closed and bounded set in the real numbers, you can always find a finite subcover. Okay. So that brings us to our next definition, compact. Now your book says this is the greatest definition in mathematics. I think it says that on page, I don't know. Yeah, actually it's the name of the chapter, the name of the section is the greatest definition in mathematics. I don't know. I mean, you could argue that maybe not. I don't know. It just depends on what you like. But the point is that compact things are really nice to work with. And so, intuitively, you can think about something being compact if you can put it in a box, I guess. And so the formal definition is if every open cover, so if your set is compact, then every open cover of your set will contain a finite subcover. And so if we look at our little picture to the left here, obviously there's not infinitely many dotted circles, but you could imagine that. You could imagine that there's infinitely many dotted circles covering this orange set. And since the orange set, if we assume that it's compact, then this definition tells us that that we can completely cover it with finitely many of these circles. We don't need infinitely many to cover it. Okay, so let's go ahead and look at this example. So we saw earlier that this open cover of 0, 4 has no finite subcover. Okay. So we asserted that before. And therefore, by the definition of compact, this can't be compact, okay? So actually I should add this. I should add 4, 0, 4. Thus, 0, 4 can't be compact. And I'll add a little note here. We'll say that, in fact, no open interval in the reals is compact. But every closed interval AB is compact. All right. So that brings us to our big theorem here, the Heine-Borel theorem. Okay, so what does it say? It says that a set is compact, okay, and we know what compact means. Every cover has a finite subcover. So a set is compact if and only if it's closed and bounded. So both of these things need to be true for a set to be compact. If one of them is not, then it's not compact. So for example, the real numbers is not compact. We have seen in examples that that the reals are closed but not bounded, right? We can't bound the real numbers. We can always find, given any real number, we can always find one larger than it, so unbounded. Any finite set is compact. I think I made a comment about this earlier, but let's prove it. So suppose we have a finite set. Is a finite set in R. And suppose that we've ordered the set just how you would think it was. So, and suppose that A1 is less than A2, blah, 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 less than A capital M. Well then, suddenly this set is bounded. Then the absolute value, well, actually, let's say it like this. We'll say that let M be the max. Alright, because if these are all negative, we might have some trouble. So let's ensure that we have the absolute value here. And define M as the max of the absolute value of A1, ... absolute value of AN. Then we have absolute value of A1 is less than or equal to M, ... all the way up to absolute value of N is less than or equal to M. And so the set is bounded. Now, so let's say, so this set is bounded. Okay. Now we need to show that it's closed. Well, by the way that we ordered these guys, we can show that it's closed by showing that the complement is open. So if we look at the complement, that's just going to be, so if we take away everything from this set that is left in the reals, we have that this is going to be negative infinity to A1, union A1 to A2, union ... union AN to infinity. Okay, and we know that a union of open intervals is open. Let's go ahead and prove the Heine-Borel theorem. Okay, so remember it says that a set is compact if and only if it's closed and bounded. So we're just going to prove the forward direction and leave the other direction as an exercise, or you can look at it in the book. Okay, so let's do the forward direction. So we're going to suppose that A is compact. And what does that mean? Actually, I'm going to call it S, just to be consistent with my notes. All right, so we're going to suppose that S is compact. And what does it mean to be compact? Then, by definition, every open cover of S has a finite subcover. All right, and so our mission here is to show that it's closed and bounded. And so we'll do bounded first. So we'll claim that S is bounded. And the proof will consider an open cover of the reals. So consider the open cover of R. And let's say this is I1, I2, ... So it's a infinite cover, and each of the INs are going to be of the form, the open interval, -n to n. Okay, and so we can see that this covers the real numbers. If we draw a picture here, here's our real numbers. And so, you know, we have I1 is -1, 1, I2 is -2, 2, etc., etc., etc. And so we have something that looks like this. We have I1, I2, I3, and so eventually we're going to cover the real numbers, right? All right, and so since this covers the reals and S is a set in the reals, it's going to definitely cover S. So let's write that out. So since S is contained in the reals, we must have that I1, I2, blah, 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 covers S as well. Okay, and now we can use compactness. So since S is compact, what does that mean? Well, it means that every open cover, we have one right here, has a finite subcover. Okay, so since S is compact, there is some finite subcover. Of I1, I2, ... that covers S. Okay, and so let's go ahead and write this subcover out. So we can say let IN1, IN2, ... INK be the subcover, and we'll say that N1 is less than N2 less than NK. Okay, so essentially we're plucking out a subsequence. Okay, and so let's go ahead and look at the picture here. I'll say that this purple part is going to be my set S. And so the idea here is that this finite subcover is going to completely cover S. Okay, so let's go ahead and draw our picture here. Let's say that, so here's my reals. Let's say that S is maybe like a piece of this and union with this, maybe. I don't know. So that's S. Maybe it's on two different, like in two different areas. It doesn't all have to be in the same area of the reals. Okay, so from our picture, if we have that IN1, or if we have that N1 is less than N2, less than N3, etc., well, what does that mean? And if this guy completely covers the set, then we have something that looks like this. So maybe this is IN1, maybe and N1 is less than N2, etc. This is IN2. And eventually it's going to cover it. So eventually we're going to have... I didn't draw this great. But... whatever. Let's see. I'll just extend it a little bit. Because I'm like trying to draw it symmetrically, but whatever. So eventually, at this nkth spot, this whole set's going to be covered, right? And also notice from the picture that IN1 is completely contained in IN2, which is completely contained in blah, 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 all the way up to INK, right? Because remember, I1 is -1 to 1, I2 is -2 to 2, and so, you know, we have this guy right here, since N1 less than N2 all the way less than NK. Okay, and so what does this tell us? Well, this tells us that S is completely contained in one of these intervals. In particular, S is in, well, we can say it like this. S is in this interval right here, which equals -NK to NK. And this means that S is bounded, right? It's bounded above by NK. Okay, so we have that piece of the proof, and the next part we need to show is that S is indeed closed. So let's go ahead and do that. Let me see. I think I'm going to run out of room, so I'm going to just go to the next page. So we're going to claim that S is closed. All right, and so the way that we're going to do this, and remember, we've assumed that S is compact. Okay, that was our underlying assumption here. The way that we're going to do this is by way of contradiction. So suppose for the sake of contradiction, that S isn't closed. That S is not closed. Okay, and so we can use Theorem 5.2 here and mess around with sequences and get a contradiction, basically, is what we're going to do. So by Theorem 5.2, then by Theorem 5.2, S doesn't contain all of its limit points, right? We had that theorem that said that S was closed if and only if it contains all of its limit points. So if it's not closed, it doesn't contain all of its limit points. Okay, so let's define a limit point that is not in the set. So we're going to suppose X is not in S, and X is a limit point of X. So what does it mean to be a limit point? That means that we have some sequence, and there's some sequence, A1, A2, A3, blah, 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 which converges to X. And each of these guys in the sequence, each AK, is in the set S. Okay, so now what we're going to do is we're going to consider an open cover of the reals without X. Okay, so consider the open cover of the reals without X. Okay, And so we're going to say that this open cover is going to be infinite. And each of these UNs are going to be of this form. It's going to be of the form negative infinity x minus 1 over n union x plus 1 over n infinity. All right, this is going to cover the entire real line without x. All right, it's never going to cover x because we can make n as large as we want, and this interval is going to converge to negative infinity comma x because this goes to 0. And likewise over here, this guy converges to 0. So as n gets really large, this thing is going to go from x to infinity. But notice that we're not including x because of these endpoints. So this completely covers the real numbers without x. Okay. So let's see. Well, since we assumed that this covers, maybe I'll just actually write it down. Well, let's see. Yeah, okay, fine. Let's just write it down like this. Since x is not an S and this guy covers R without x, then certainly it covers S, right? Because S is a subset of the reals, and this is going to completely cover everything except x, so it's definitely going to cover S. Okay, but S is compact. Okay, so we're going to do the same kind of trick that we used to show boundedness. Since S is compact, this open cover has a finite subcover that covers S. Okay, so since S is compact, okay, and so let's again do the indexing with the n1 through nk. Say that u n1, u n2, dot dot dot, u nk, where n1 less than n2 less than dot 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 less than nk. So we're gonna notice that we have the same thing when we were trying to show boundedness, that we have un1 contained in un2 contained in dot 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 unk, and so S is completely contained in unk. We can draw a picture here. Okay, so we have negative infinity to x minus 1 over nk, and then x plus 1 over nk, all the way to infinity. Okay, and so our set S is going to be in purple. Maybe it's somewhere in here and here. It's completely contained in there. And this guy is going to be x, and this guy is our neighborhood, x minus 1 over nk, to x plus 1 over nk. And notice that this intersected with S is going to be empty. And this is going to give us a contradiction. Okay, and so to see the contradiction, we assumed that our sequence AK converged to X, and so that means that for all epsilon bigger than 0, there's some capital N, such that K larger than capital N is going to imply that A sub K minus X is going to be less than epsilon. And so our properties of absolute value tells us that this means that AK is between x minus epsilon and x plus epsilon. Okay, so that means that AK is in this neighborhood. But this is where the contradiction arises. Okay, so let epsilon equals 1 over nk, and then we have the contradiction. We have that AK is going to be in x minus 1 over nk, x plus 1 over nk, and we said no, actually all of these terms in our sequence are going to be in S, okay? And so that's the issue here, right? Each of these AKs was in S, but since this guy, this AK is in this neighborhood, which intersected with S, which is the purple, is empty, this is going to give us the contradiction here. Okay, contradiction. Therefore, our set S is closed. All right, and as I mentioned, if you want to see the backward direction, that's going to be pages 161 through 162 in the Cummings textbook. All right, I hope you guys enjoyed this video. Thanks for watching, and see you guys next time.